couple things before returning to the end of airplanes, really. Question just came in about problem set, dropping the lowest problem set score. Just let me remind you that my deal is if you complete the course evaluation run by the university, not by me, for this class, I drop your lowest problem set score, just incentive to do it. And those evaluations show up sometime after, I believe after Thanksgiving, and I think you get an email prompting you to do this. It's on Colab. You don't log into a course. It's right there when you first sign into Colab. And there's a hard deadline that they usually make 11:59 p.m. somewhere, so it's not ambiguous what day it ends. But it's a hard deadline. Once that passes, it's over. And it's well before the final exam itself. I don't know what determines the starting and stopping day of those evaluations. It's like a 1-week period. That's one thing. Second thing, the midterms, I meant to put out the booklets and stuff. If I have time before I get booted out because of the football game, I will try to put the midterms out in the boxes. Otherwise, it'll be over the weekend and email you guys. Third thing is I'll put up the remaining problem, the next problem set this afternoon also after class. I hesitate to put it up before the previous problem set's due for fear I will, no, not for fear, knowing that I will get people who are loosely connected to this class going in and completing the wrong problem set and not even realizing that we haven't covered the material yet. It's always a little humorous, but only a little. What else? I posted, alas, I have posted the wood stove video, but pretty late, like an hour ago, I think. So I'll do what I can to make it up. Other logistical questions, sort of not topic, not physics questions, things you care about. I do encourage you to come to the office hours. If those of you who are concerned about your midterms and stuff like that, come talk to me. Well, our office hours are right after class. Just we can chat for a while. Yes, Sophie? The next problem set, not anymore, it's due Friday. Okay, I put it back to Friday because I won't get to the material again. You know, it's a little tight. Okay, so it's based on issues of wood stoves, the flow of heat, and to some extent on how water behaves, water, steam, and ice. So I need both those topics, and we'll get to them. But other questions? Yeah, Alex? I'm not teaching 1060 next semester, no. Gordon Cates is. Well, normally it would be a year beyond that. We'll see whether the teaching committee cycles me back into doing it. It's a little unclear. All right? Other questions? All right. Yeah, so some questions that came at the end of last hour and I never got to. How an airplane flies, the wings and deflecting the airstream and so on, and trying to be streamlined. Is that how animals fly? And the answer is absolutely. They have additional complexities. Like there's this story about how a bumblebee can't actually fly, and but it does. It's okay. So there's some complexity, and they do take advantage of features that you don't normally see in airplanes. Airplanes do not normally flap their wings, but things like most birds, first of all, they're streamlined. They're doing their best to get as little pressure drag as possible. They try to control the flow of air. They deflect the air. They work. I'm sure that they develop low pressure on top of their wings when they are normally flying, and high pressure below it. And they try to keep turbulence off the tops of the wings, things like that. And their steering, they turn by tilting is just the same as an airplane does. They don't just simply turn and fly, therefore slip sideways through the air. It's not, it's a bad move for planes. It's a bad move for birds. Regarding the loss of roofs during windstorms, as the air goes over the top, just to remind you this, as the air goes over the top of the roof, a peaked roof, not a flat roof. So a peaked roof, there's a bend toward the roof, which I hope at this point you're comfortable with the idea that if the air is bending toward the roof, it's being pushed toward the roof. And that means that the pressures between just above the roof and far, far, far away from the roof where it's atmospheric, those pressures have to be different, and the lower pressure is just above the roof. So there's a push toward the roof. So that's low pressure right above the roof, high pressure in the attic. That creates a lift force on the roof. And the lift force is upward vertical because if you've got the higher pressure is below the skin of the roof and the lower pressure is above the skin of the roof, that's a pressure difference across the shingles and all that stuff. And the pressure difference is pushing up harder than it's pushing down. And that's a net upward force, I mean, apart from gravity. And if it's bigger than the weight of the roof, up goes the roof. Is that okay? Issue of defects in trying to control the airflow over the wings. Airplanes clearly are built to tolerate some amount of imperfection in the surfaces of the wings, the surfaces of the aircraft itself. They obviously fly after damage. Surely as things get damaged, they develop more drag, and they probably lose some amount of their lift, or certainly their control over their lift, but they can tolerate a lot of trouble. The idea of defects being all bad is also not quite right, because sometimes you actually want, in effect, defects, although you usually control them. What I'm thinking about is this, that sometimes if you look out at the wing of an airplane, you will see that the wing actually has structure on it. You have typically little projections sticking up from the wing at even intervals of maybe a foot or two. And those are the ones I have in mind in particular are known as vortex generators, and their job is to trip the boundary layer like the dimple of a golf ball to get a little bit of tumbling going in the boundary layer flow over the wing. Now, why would you want to do that? Well, in a golf ball, if you remember, the playing with the boundary layer and letting it tumble allows the overall airflow, the main airflow, to stick better to the back of the ball, break away later, and make a smaller turbulent air pocket. So it's a good thing to trip the boundary layer in that context. And it actually turns out to be a good thing, and certainly in some airplanes. They deliberately trip the boundary layer, they get some tumbling going. So the airflow makes it to the back of the wing the back top of the wing more easily, and is less likely to stall, to break away from the surface of the wing. So the plane can fly better, more safely. They also use other tricks to try to make sure that that airflow on the top of the wing stays attached, doesn't make a turbulent wake. Associated with, well, I won't go into the details of that. Anything else about it? Yeah, David?
The golf ball, if it was going to be laminar flow, you wouldn't want to have the dimples?
If the golf ball could maintain laminar flow, regardless, you would not want the dimples. They're only there because you're going to get turbulence. No matter, it's a for sure thing on a golf ball. It goes too fast, has viscosity that's too low, you're going to lose. So control the turbulence, and they shrink it as much as they can with the help of the dimples. Other thoughts? Actually, another observation about animals. Birds in the air is the obvious thing to think about in terms of fly like a plane. But actually, things fly in the water as well. And an example of a machine that flies in the water, oddly enough, is a submarine. Submarines try to achieve approximately neutral buoyance. They try to actually weigh about the same amount as the water they displace. Pretty close. And they're actually a very interesting topic I used to include in this class way back. But okay, but they're mostly very close to being just the same weight as the water they displace, and therefore it takes relatively little force to accelerate them upward or accelerate them downward. So how do they accelerate upward and downward? Well, not by playing with their buoyancy, but by playing with wings. They have wings on the projections coming out of the sides of the submarine that are wings, and they fly in the water. And you want to move up or accelerate upward, you tip the wings angle of attack high as you're heading forward, and up it goes. You want to go down? Tip the wings low and get downward lift, and go down. So having said that, then, the shaping of a submarine is for the most part, is driven by need to not get smushed. So that you can't make a submarine that's a box. It has to be a cylinder, and the ends matter because the pressure is just so tremendous on the submarine that it doesn't have a lot of choice. But in general, if you're moving through the water, and you want to minimize drag, for example, you want to be as streamlined as possible, an approach is to imitate animals. So for example, a dolphin or a shark, these animals have evolved to be remarkably streamlined. They leave incredibly small wakes behind them. Therefore, they can propel themselves through the water way faster than most things you would imagine building, because they're just able to just maintain laminar flow, really control the flow well. And I suppose people have been trying to imitate fish, like for swimmers. There was this era when people started wearing special suits that sort of changed the shape of a person so they could swim faster. And I guess there were battles whether that was legal or illegal. Was that going to be allowed in swimming? I mean, pretty soon people would be swimming in dolphin suits. I guess eventually that got banned from competitive swimming. But fun and games. Actually, related to that, bicycling, you can only bicycle so fast if you're a lone bicyclist because of these aerodynamic forces, particularly pressure drag. So if you want to reduce pressure drag, if the rules of whatever your situation allow it, wear a suit, essentially, that allows the air to flow streamline around you. And those are called fairings. And people do experiment or play with fairings. I mean, it's not a suit. It's a change in the shape of the bicycle. And you bicycle within this structure called the fairing. And people doing this can go 60 miles an hour, I guess. I don't know what the record bicycling speed is, but it's somewhere in that territory. 60 miles an hour. You cannot bicycle 60 miles an hour without that. The pressure drag is just hopeless. But if you get rid of most of the pressure drag, you can do it. All right? Yeah, Sophie. What happens when an airplane flies through turbulent air? So the lift is all predicated on the idea that the airflow around you is smooth, laminar, everything's simple. If the air itself is tumbling when you're going through it, 2 layers of air, for example, rubbing across each other and just becomes unstable and it tumbles, then the airflow across the wings is coming from sort of random directions. Sometimes it's sitting there motionless as you go through it. Sometimes it's moving down. Sometimes it's moving up. And so you get unpredictable lift, and furthermore, it's not even uniform across the whole plane. This wing can be getting upward. The air might be going upward here and downward there. And so it's erratic, and that's why the plane kind of bounces around. The lift force is fluctuating, and it's fluctuating locally. Is that okay? A little connected to that is airplanes leave behind them turbulence. It's a little more predictable than weather turbulence. The weather turbulence is, and going through clouds in particular, are full of turbulence. That's unpredictable. What planes leave behind them is relatively predictable. They leave vortices behind them. And a key source of the vortices are the 2 wing tips. So that at the tip of the wing, imagine the drawings that I showed you earlier and that are in the book and so on, sort of a slice through the wing. There's a slice through the wing maybe near its middle. But the wing isn't infinitely long at either end, and so life is a little more complicated at the ends. And in particular, at the open end of the wing, say the left wing, if I'm flying toward you, the left wing, when it ends, it has the low pressure, the high pressure below it, the low pressure above it, at least in principle. Well, high pressure down here, low pressure there, the air can scoot around the side of the wing and sneak from below to above. And it would love to do that, and it does, right? It's sort of low pressure down, high pressure down here, low pressure up here. That works well in the middle of the wing, but at the ends, there's a shortcut. So the air sneaks around, and as it sneaks around, that arcing over is a rotary motion, and the air continues to sort of arc around there behind the plane, and the plane leaves behind it a swirling little tornado, a vortex, with a center. It looks like a tornado if you could see it. Sometimes you can see it if the humidity is just right. You can actually see the wingtip vortices left behind a plane, and I guess I could try to track them down, but I won't do that right at this moment. So there are two tornadoes that roar off behind the plane, and they take energy out of the plane, so they're not desirable for the plane itself. And a solution to this is the little winglets that you've seen on some planes that stick up. That's there in part to shrink the wingtip vortices, take less energy out of the plane. The other feature of the wingtip vortices is when you fly into them in a second plane, it's an experience. If it's a big plane, and years ago I was in a DC-10 following another DC-10, and we hit the wingtip vortices of the leading DC-10 twice, not just once, which was bad enough, twice. And the plane just abruptly goes, whoo, just suddenly tips 20 degrees in 1 second, half a second. It's much worse in a little plane. My father used to fly little planes. They apparently went all the way to 90 degrees behind the wingtip vortice. So they're no fun to hit from behind. This is one of the reasons why planes take off every 90 seconds from airports, not every 60 seconds or 30. The wingtip vortices are there. They gradually descend for some reason, which I can't offhand think of. And so you want them to sort of fall away and then not fly through them. They actually make sound too as they come by. So if you stand below a landing strip, the front of a landing strip, the planes are coming in, you can hear them. You hear the sound go by. What else about them? If you come across them the other way, they're like a speed bump. So I've done that at least once before, where you just boom. What was that? What did we just hit? Is there a bird out there? No, you just hit a wingtip vortex. Is that okay? It is what it is. They're there. Right. Yeah. Yeah, whose phone is this? Yeah, that kind of stuff. All right. Let me say some last things about airplanes that I left behind last time, apart from these details. And that is jet engines. Why jet engines? Propellers were great and are great for relatively low-speed planes, where essentially you can approximate the air's behavior as it's just sitting there, and the propeller is, as I say, a rotating wing, and I hope that makes some sense, and I'm not going to dwell on it much longer. But as it sweeps through the air, it's trying to fly through the air such that it gets lift in the forward direction to propel the plane forward, in which case the lift is called thrust, just to give it a name that seems more relevant. And I can say also that if you take the propeller and turn it vertically and spin it around like this, as a wing that's whizzing around, you've reinvented a helicopter or a drone. That's how they work. Again, it's a spinning wing, moving through the air deliberately and flying and developing lift and supporting. But going back to a normal propeller, once the plane starts going fairly fast, the air that the propeller is working in is coming at the plane, maybe 100 miles an hour. And now the propeller has to adjust a little bit because the air's coming at it. The angle of attack it develops by sweeping through the air changes because the air is moving. And at 100 miles an hour, it's not a big problem. Typically, they want to pivot the propeller a little bit to change its angle of attack to get the best lift/thrust force. But by the time you get to about 300 miles an hour, life is getting really tough. The air's coming at the propeller so fast, the propeller's having a tough time essentially keeping up with it. And my analogy to this is that suppose you're swimming. If you're just swimming along in normal speed, you reach out, grab the water, throw it backwards, reach out, grab the water, throw it backwards. It's not really a problem. But as you start to go 10 miles an hour, now reaching in, you have to go at least 10 miles an hour throwing back, or you just break even or worse. And if you're going 100 miles an hour, you're going to have to move your hand back so fast, you just can't do it. And the same thing happens for the plane. There comes a point where the air is coming at the propeller so fast, the angle of attack becomes terrible. They can't get any lift out of it. And a possibility is to spin the propeller faster and faster and faster, but that runs into trouble when the tips of the propeller start going the speed of sound, which is in the vicinity of 750 miles an hour. Those propeller tips start to have trouble for all kinds of reasons. That in effect, you just can't run a propeller on a plane that's going more than about 300 miles an hour. All sorts of bad things happen. They have worked on these kind of propellers, but it's generally a losing battle. So what can you do? Well, you shift over to a jet engine. And the way a jet engine works is it uses Bernoulli stuff, right and left. The air entering a jet engine slows down by going into a duct, which is basically a diffuser. They let the air slow down, spread out. It actually, because air is a compressible fluid in reality, life is a little more complicated. But basically, from the perspective of the plane, they take this onrushing air at, say, 600 miles an hour, they slow it down in a diffuser, the pressure rises, the kinetic energy drops, they trade off. They then send that air, they actually send it through a compressing system, a set of fans that compress the air. They burn fuel in it, and then they send it out a nozzle. And the nozzle, which includes turbines to run the compressor. But the main point is, they take air in at relatively low speed. They work on it to get it up to high pressure, high density. That activity is done on relatively low speed air. It would be hard to compress air that's moving 600 miles an hour, but it's doable when it's down to 200 miles an hour or something like that. So slowing the air down is really helpful. They then burn fuel in it, and then they send out a nozzle. The best way I've figured out how to explain why this whole process leads to a net propulsion of the plane is that when they burn the fuel, it gets so hot, and the molecules and stuff break up into smaller pieces. So not only does it get really hot and therefore have a tendency to occupy more space, to expand, but it also has more particles than it used to. So it has a tendency to want to expand further, because remember, particle density is what determines pressure in a gas. So they're taking gas in basically through essentially a narrow pipe, and they're sending it out through a wide pipe, having made more volume of gas. They enlarge the volume of the gas by burning fuel in it and breaking it up into little pieces. So it's almost like they created gas out of nothing. It's not totally true. They have to take in air up front, but the amount of gas they're throwing out the back in terms of volume is much larger than the volume of gas they're taking in from the front. So they're a little bit like a rocket, where they start with something on board. It's not really on board. Some of it is the fuel, but the air that comes in is sort of coming in through a little pipe, and you can almost ignore it. And then they're throwing the whole mess that they create out the back at tremendous speed through a nozzle. And the result is, if you push it out through the nozzle, it pushes you forward. And it really, the forward thrust is on the combustion chamber, the front of the combustion chamber, where they are creating more volume in there at very high pressure. There's a huge forward push on the combustion chamber that is not canceled by anything else. And that throws the plane forward. Is that okay? Good enough? A detail I'll add is that concept where you take in air, burn fuel in it, and then just pour this greatly enlarged air out the back of the nozzle. It's a great idea, and it was used, I suppose, in World War II. That's when jet engines first sort of showed up. It's energy inefficient because you're throwing too little mass out the back at too high a speed. That's not a good idea. If you want to, because the faster you throw the stuff backwards, the more energy it's carrying with it in kinetic energy per kilogram. Because remember, kinetic energy goes as the square of speed. So going to very high speeds is a bad idea in terms of energy. You get too much energy in it. So you want to throw more mass backwards at lower speed instead of less mass backward at higher speed. How do you do that? They run a fan. They use the turbojet engine as the power source, as the rotary power source for a giant fan. And you've seen these on planes too, where the engine is big enough around for someone to stand in it. There's this huge fan structure there. And the turbojet engine is spinning this baby. It's the center core. But most of the air goes into the duct and slows down, has work done out by the fan, to add energy to it, comes out the back, and then goes through a nozzle and speeds up. And the added energy means that it leaves going faster than it entered. So there's a net forward thrust on the plane. And because it's such a huge fan and it gathers so much air every second and gives it, I would say, a gentle push backwards. The air coming out of the fan is going faster backwards, but not dramatically faster than it entered. So you're pushing a lot of mass at a lower speed. You get the momentum you need to move forward without pouring energy into that passing air, wasting energy in the passing air. So all the jet aircraft you've flown in, if you haven't flown in antiques, they've all been turbofan engine driven. They all have a turbojet at the core, a fan at the outside. Is that okay? I thought otherwise in one of the versions of this book, and someone in the industry, an expert and a historian, said, no, nobody flies turbojets anymore. They're gone. They're just too energy inefficient. All right, I think with that I'll stop airplanes. Any other questions about airplanes? Took a while, all right. How is fuel used in a jet engine? It is injected into the passing air. So the air goes into the jet engine. This is the turbojet part. The air goes in, slows down, is compressed by fan blades to high pressure. Fuel is injected into it, and then it's lit on fire. So there's a roaring flame, which you do not get to see, inside the jet engine. I mean, this is one of these things like if actually there was a little, they could put a little glass housing so you could see it, and it would scare the out of you, right? There's a flame in there. Well, there's a roaring flame going on inside there. And then they run that gas, that hot gas. They're making huge volumes of hot gas now. As a result, they run it through turbines, which is, again, fans, but fans that don't do work on the air. They have work done on them. They are run by the passing gas. Those power the compressor. And in a turbofan engine, they power the fan. And then the air comes out, having lost a little of its energy to the turbines, and then it goes through a nozzle, where it speeds up and its pressure drops, and it comes roaring out of there at tremendous speed. And you've seen this, if you watch the contrails, the condensation trails of jet aircraft going over, if you watch just behind the engine, behind the plane, the gas moves very fast initially. It's like shooting out of a nozzle, and then it slows down and becomes puffy and white. So watch the passing planes and see how fast the gas is coming out for the first 100 feet behind the plane. It's just roaring out of those engines, and that's the propulsion. So yes, the fuel is a roaring flame. It is designed to be easily ignited because you want it just to burn fast as possible. It turns out that'll be reverse for automobile engines. Internal combustion engines, they deliberately make the fuel difficult to ignite for good reason. The more difficult it is to ignite, the higher its octane is, and premium gasoline is particularly hard to ignite for good reason, and we'll do that in a week or two. What happens when a bird goes into a turbine? The turbines are designed to ingest a fair amount of birds without significant damage. And I doubt anything identifiable comes out. I mean, just gas. They're gone. The turbines are actually amazing things in themselves. A lot of them are single crystals of a metal. They're under such stress at such high temperatures, and they're spinning so fast. They have to be incredibly strong, and so they are tour de forces these days. They're just amazing. I don't know, mixed languages, but anyway, it's they obviously tolerate a lot of stuff going in, with exceptions. So the emergency landing, the famous emergency landing in the Hudson River in New York, with the pilot whose name I can no longer remember, Sully. That ingested an awful lot of birds on both engines, and then the engines both stopped turning. I don't know whether they were actually structurally damaged. I mean, landing in water surely was not good for them, but Yeah, they're meant to tolerate a fair amount of abuse without damage. Same with the windows of the aircraft. The windows of the aircraft are also another amazing thing because they have, you know, bird hits them at 600 miles an hour. It's not good for the windows. I have seen a plane that had to come in for emergency landing that had taken a good bird strike, and it just the windshield was like, it was really shattered, but intact enough that you know, it wasn't like the wind was flying around the cockpit, but they were not happy. It was just definitely, you know, big damage to that window. All right. Wood stoves. So wood stoves is a real change in the focus to the movement of thermal energy. And to try not to completely repeat my own lecture video, the idea with a wood stove is that you're burning a fuel, in this case wood rather than aviation fuel. You're burning wood in the presence of oxygen air in the air, releasing thermal energy, and I'll go back and look at that in a minute. And then you end up creating a very hot region. And again, what does it mean to be hot? Temperature, all that, I'll come back to that too. And then that thermal energy will migrate into the room, because that's the point, is to heat the room. And how does it migrate? So look at where the thermal energy originates from, how it migrates, and I guess a little bit at how the room gets hotter as a result. Okay, so that's sort of the story. And to begin with, where does the thermal energy come from? The thermal energy started the story as chemical potential energy in the wood and the oxygen in the air. You need them both, and you know this from long past experience. And so what exactly is chemical potential energy? And in fact, so the story of chemicals a little bit. So here's in a nutshell, the chemical potential energy story. And that is this, that suppose you have two atoms, and we won't this semester look at the structure of atoms, but they're the tiny little particles, as you well know. They're complicated if you actually look into the details. But the general idea is if you've got two atoms that are far apart, they're very far apart, they don't care about each other to speak of. But as you begin to bring them together, the first thing that develops between the two is an attraction. All atoms, pick any atom and any other atom, two atoms, as you bring them together, they will begin to attract each other at distance. So there's an attraction, and then the attraction reaches a peak. That's the strongest attraction. And then as you get closer still, the attraction gets weaker until finally there's a distance of separation at which the attraction drops to zero. And then it becomes repulsion. They push apart. So the overall theme is, and there may be some funny structures in it, but the basic theme is they attract up for a certain distance, they hit zero, and then they repel beyond that. And if you grab two atoms with tweezers, as if, and you let them come toward each other, if you release them, they'll attract, go faster and faster, and they'll bounce off each other. Don't do that. Let's grab them with tweezers and let them drag our tweezers toward each other, during which time they're doing work on us. Right? They're pulling on our tweezers. As our tweezers move in the direction of the pull, they're doing work on us, giving us energy. I wonder where that energy is coming from. And we let them get right to the point where they stop attracting each other. They're right at that neutral point, and we take the tweezers off and let go. They're stuck. They're now at an equilibrium separation. They neither attract nor repel, and it's actually a stable equilibrium. If you go in there and you nudge them, they'll bounce back and forth about that equilibrium a little bit and settle. And that's molecular vibrations. This is what's associated with the molecular vibrations, is the bouncing back and forth about the equilibrium. But they like to be at the equilibrium. Life is a little complicated because this is all entwined with quantum physics, which I won't do. So the energy that the work they did on me in coming together, when I let go and just released them and walked away, I stole their energy. They're stuck together now until somebody, me or somebody else, comes and repays that energy. They have a deficit. They're glued together by a deficit of energy. Because again, if you want to get them apart, you have to pull. because they attract as soon as you get a little separation, a little additional separation. You have to rip them apart. So that deficit of energy is the chemical bond. That's the origin of it. So all your studies of chemistry and whatever, when they talk about chemical bonds and all that, and there's lots of details that are interesting in that, but the basic underlying issue is it's a deficit of energy. When the two came together, you have to pay to pull them apart. Is that okay? Now, different atoms will release different amounts of energy in coming together, and different assemblies of atoms, so-called molecules, will have also release different amounts of energy. And it is possible to bring together a big collection of atoms, pick a certain collection, bring them together in a certain organization, have them release energy, and now be held together by chemical bonds. Everything's good. Life is simple. They're all sitting there at equilibrium. And now, if I were to come in and rearrange them into a new configuration of molecules, they would release even more energy. There's a new way of organizing them where they're happier even. They will have done more work in the process of rearranging and release more energy. And what I'm thinking here, and what my motivation is that the chemicals in wood and oxygen in the air are in the first situation where they've released energy, they're bound together in various ways, they're all at equilibrium, everything's good, but you can rearrange them into a new configuration that will release still more energy, and that's the burning process. So the burning process takes wood and oxygen, rearranges the molecules primarily into water and carbon dioxide, and still more energy comes out. The new molecules that you formed are even more strongly bound together, meaning you have to pay even more energy to rip them apart. The water molecule is a pretty happy little character. To separate all the pieces takes a lot of work. Same with carbon dioxide. It's hard to disassemble that one too. A lot of energy necessary. So what burning does is it takes chemicals that were relatively happy and makes them even happier by allowing them to rearrange still further and be bound even more strongly. Is it okay? The process of rearranging, in this case, from wood and oxygen to water and carbon dioxide, doesn't happen spontaneously at room temperature. Why? Because to get the rearrangement to the the final arrangement, you have to break apart the initial molecules to some extent. They were quite happy with each other in their first configuration. You have to nudge them to get them to discover the new possibility, the post-burning possibility. And that energy that you invest, you have to invest energy to get the rearrangement started, at which point extra energy comes back. And that invested energy is just called an activation energy. This is why you have to light the fire. You're putting in energy with a hot flame that gets the combustion reactions to start by partly disassembling the original chemicals. Is that okay? Yeah, Serena. Can you undo the burning process, basically? So Serena's question is, so if you're taking wood and oxygen and you rearrange them to create carbon dioxide and water, can you undo that? In principle, all the energy is there. When you do this, it releases energy. And if you do this in a closed, sealed box, in isolation, all the energy you started with is still there. It's now in the form of thermal energy instead of chemical potential energy. And in principle, it can go backwards, because the energy's there, everything, the particles there, everything's there, it's just got to undo. It doesn't happen for statistical reasons. You can't unburn stuff because it's statistically impossible. It's just, I would say unlikely, but it's so unlikely it never happens. It's like when you smash a vase, a glass vase, it's all still there. And in principle, you could pick it up and drop it a second time and it reassembles. But it never happens statistically. It's just too unlikely. Is that okay so far? That set aside, plants do exactly that. Where did the wood come from? it came from the plants taking in water and carbon dioxide, using energy that they got from the sun, and it reassembles wood and spits out oxygen. So it unburns, but it's not doing it just using lucky statistics. It's driven by heat from light from the sun. So to undo the broken vase, you can undo it. If you have to bring in something new into it. And actually, what's really being brought in is order. When you smash the vase, you lose order. It's disordered now. To undo the disordering, you need to bring order in from somewhere else. Like, a fix-it person, a glass blower melts it all down and brings in fuel and stuff. So the order came in with the person. In the case of the plant, the order came in from the sun. And we'll see that, so the sunlight is bringing energy, it's also bringing order with it. Is that okay? We'll see that's the story of thermodynamics, which we'll come to when we look at air conditioners and automobiles. All right? Hi, thanks. So that's the origin of the thermal energy that comes roaring out of the wood stove. How about the act of having it come out? And it turns out that the thermal energy comes out of the wood stove, not with the smoke and so on of the stove. One of the values of a wood stove, of course, is it burns the wood inside a box and sends the stinky stuff out for the neighbors to enjoy. You only get the thermal energy out into the room. And why in general does the thermal energy come out of there? Why doesn't it just stay inside the box? And the general observation is that thermal energy naturally, and for statistical reasons, as we'll see, it naturally flows from hotter to colder. And actually temperature is the concept is defined by the direction in which energy flows spontaneously. I'm a little off on a tangent that I'll try to reel in, but basically, if you've got something that has a high temperature, which is the inside of the firebox inside the wood stove, and you got something that's got a lower temperature, namely the room air, heat naturally flows from the hotter one to the colder one. And when it does that, and it's doing this again for statistical reasons, which we'll come to down the road, that thermal energy on the move is given a new name. It's called heat. So I used to be cavalier about this, and then in the era before I wrote the textbook, and then once I wrote the textbook, the purists, or I don't know what to call them, the people who are adamant about naming things correctly said, no, you can't do it like that. So the idea is, an object has thermal energy in it, just like it has the ordered energies we've talked about. So you can have energy, but when it moves from one object to another, we give it a new name. In the world of ordered energy moves from object to object by doing work. That's old story. That's how you move it around. So energy on the move is called, mechanical energy on the work, ordered energy on the move is called work. Thermal energy on the move is called heat. Just to give it that, this is the official naming. And so when energy flows from one object to another because of the temperature difference in them, it's called heat. So technically you don't have heat any more than you have work. Do I care a lot? No. But heat is, anyway, so heat flows from hot to cold. Is that okay? So heat wants to do this. This is its reason for it existing. The issue then is, how does the heat actually flow from the hot burns stuff in the firebox to the room air? And it flows by the three famous mechanisms of heat transfer, which you surely have bumped into at some point in your education. They are conduction, convection, and radiation. And so my goal is to make clear those three heat transfer mechanisms so they're more than just words. All right? So I'll follow them in that order, actually. The first two are pretty straightforward. The last one's a little mysterious. Radiation, what the heck is that? It's a catch-all word, furthermore. radiation in general is anything on the move. So this is baseball radiation, okay? People are all worried about radiation. That was not very dangerous radiation. Okay, conduction. Thermal conduction is the flow of heat from hot to cold through a material where the material itself doesn't physically move. It's not going anywhere. So it's heat flowing through a material without the material going. Convection, as we'll see, is heat flowing with a material that is moving like a fluid. I mean, it's essentially always applied to a fluid. You can heat water and then move the water. That's convection. Radiation is thermal energy traveling by way of electromagnetic waves, which include light. So we'll come to that. Just to try to be efficient with the last couple of minutes here, I'm not going to be able to show you properly conduction, but I can. You remember my rule? Any excuse for liquid nitrogen is a good excuse. All right. So heat. What does this have to do with conduction? Conductive heat transfer, at its most simplest component of conductive heat transfer is when you have a hot object, one object with a hot end and a cold end. And at the hot end, the thermal motion, the jittering of atoms because they have thermal energy, is more aggressive than at the cold end. And just by statistics, the bumping and jostling that goes on in the hot end tends to transfer some of that jostling energy, the thermal energy, to the adjacent section that's a little colder, and to the next section that's a little colder. And that works its way all the way through the material. So when I take this room temperature rubber ball and put it into that rather cold liquid nitrogen, heat is now, so this is my excuse, heat is now flowing by conduction through the rubber, by jostling. The inner core of that rubber ball is the hottest still. And so heat is migrating by bumping and jostling out to the outside of the ball, the outer surface, where it then jostles its way into the liquid nitrogen, which is the coldest thing in the story. So the result is the heat is leaving the room temperature, inner surface of the ball, and migrating into the liquid nitrogen, and it's just, they're all approaching the same temperature, at which point they'll be in thermal equilibrium, if I didn't use that term yet. Thermal equilibrium is when no heat flows between two objects. And it's equivalent to saying they're at the same temperature. So we've got the liquid nitrogen and the ball now are at the same temperature. Since the liquid nitrogen is sort of self-regulating at 77 Kelvin or 78 Kelvin, the ball is also at 78 Kelvin. All right, so it's cold. And it used to be a normal handball. Oops. Yeah. Once it thaws out, it'll be back normal. So now heat is going in part by conduction back into the ball. The jostling is getting more aggressive and everything like that. During the time, just for your own knowledge, rubber is a really amazing class of materials that the molecules are very mobile relative to each other at room temperature. They are just pinned to each other in a way that forbids them from actually moving long distances relative to each other. So they have a fixed shape, but there are a lot of mobility, and that gives them their stretchy and bounciness. By taking out the thermal energy, we got them to stick to each other in a way that they no longer had that local mobility. They became frozen in place, like a glass. And while they were in that glassy state, they're very brittle. All right, with that then, we'll call it a day and continue on Monday.